Hey folks, welcome to this lesson on percent yield when we're talking about stoichiometry and quantities in chemical reactions. So before we begin, let's refresh our memory as to how we got here. We were talking about stoichiometry and particularly looking at the limiting reagent. So the limiting reagent is the reagent or the reactant, limiting reactant, reagent, same thing, is the thing that controls the reaction. It's the thing that gets consumed and it controls how much product and other reactants are going to be used up. So how much product is made and how much of the other reactants are used up. Now remember from our example that the reactant that produces the least amount of product is going to be the limiting reagent. So if you don't remember that, go back to the original lesson that explains the overview of limiting reagents, and we gave you the example of the packaged meals. So in that particular case, the cookies were the limiting reagent because it produced less packaged meals than if we were just focusing on the sandwiches or the oranges. Now, that is required because it's going to be leading to the thing that we call the theoretical yield. And the theoretical yield is the maximum amount of product that can be made from a reaction in a perfect world. So if all the stars align and there's no errors, no nothing, and it's just absolutely perfect, this is the maximum amount of product that you can make. And it really is a theoretical calculation, hence the word theoretical yield. It's deduced by pencil and paper and calculated method, right? So it is a calculated thing. Now, when it comes to doing that experiment with those starting reactants, you will eventually try to isolate some kind of product. That product is going to be our focus. And how much of that product you're going to get is going to be called the actual yield. So the actual yield is how much you actually get. And you can't calculate this. It has to be done through experimentation, or it has to be given to you in a question. That's the only way that you can find this. There's no way of calculating actual yield if you haven't already either gotten the percent yield or you haven't done the lab itself. Now, the actual yield, again, is our lab yield. You'll hear, if you're reading a question, you'll hear keywords like things like isolated, right? Isolated or measured or obtained, right? These are key words that when you're reading a question is going to be hinting you that this amount that they're giving you is the actual yield that was produced from doing this lab. Now think about percent yield. Percent yield is a very simple concept. It's like a test. Let's say, for example, you had a test and the test was out of 10. Now 10 is really your theoretical yield. That's the maximum that you can get on that assessment, that test, whatever you want to call it. That's you going in, you're sitting down to write it, you can get a maximum of 10 points. Now you do it, some things happen, maybe you forgot, you didn't study that, and you got 8. All right. Now this is your actual yield. That's your actual yield. That's what you actually got out of the maximum 10 that you could potentially get. So your actual yield divided by your theoretical yield is really what gives us our percent yield, right? So 8 out of 10 times 100 is going to be 80%. That is your percent yield. And that's all that is. There's nothing more complicated to that. It's just what you actually got versus the maximum that you could have gotten divided by each other times 100, and you get a percentage. So as I mentioned, your theoretical yield is really your perfect situation. Now, what would make a situation not perfect? There's a lot of different things. So for example, some of the reactants aren't consumed in the way that you have. They got stuck to the vessel that you were transferring from one to the other. There might be side reactions, which we haven't really learned about right now. But for example, if you burn something in oxygen, you might also having a side reaction with the nitrogen in the air that takes some of the reactant and doesn't turn into the product that you would expect it to be. It might turn into a gas and leave your reaction vessel. You might also have reverse reactions. This is something that we'll learn next year, where we have something called equilibrium in some cases, where some reactants turn to product, which is what we want. But then again, when that product is formed, it can turn back into the reactants. And that's not something that we want, right? So we might not get all of our reactants converting into products. And again, there's also always the thing about losses. Now, if you sneeze into the collection container for the powder that you're collecting, that is not going to be an error. That's just you need to do that all over again, right? So keep that in mind. But again, losses could be when you're transferring from one thing to another. Some get stuck on your scapula or whatnot. So there are those things there. Now, to calculate percent yield, just like in the example of the test, you find out your actual yield by doing it. You calculate your theoretical yield, and part of that is also calculating your limiting reagent. Recall that anytime we calculate limiting reagent, we also have to have a balanced equation. So we're always going to be starting off with a balanced equation. We're going to be finding our limiting reagent, our limiting reactant, and then calculating our theoretical yield. Once we have that, we're going to compare our actual yield to our theoretical yield, and that will be our percent yield. So let's do an example just to get an idea of how this is. So iron pyrites reacts with oxygen in this particular equation, and our starting reactants, we had 300 grams of iron pyrites, and we had 200 grams of oxygen. Now notice they also give us another number, 143 grams of iron 3 oxide is produced. Okay, there's a key word there, produced. So this 143 of iron oxide, which is a product, you can see it right there, is probably going to be our actual yield. This is going to be that actual yield. So this is two things. Number one, we have this, so we can calculate our percent yield. That's number one. Number two is that remember that when we were looking for our limiting reagent, we had to choose a product to compare. Because recall, the limiting reagent is the reagent that produces the least amount of product. So we chose a product to compare, and we saw which reactant produced the least amount of that product, and that one was called our limiting reagent. So when it comes to choosing a product to compare, be sure to choose iron 3 oxide because that will make sure that you won't have to do any other calculations and your life will be a lot easier. So let's kind of put this into play. First things first, let's check out our equation and make sure that it's balanced. So I can see right off the bat that it's not. And what I notice is that here we have 3 oxygens on our right side. So, and there's no odd number of oxygens on the left. So what we're going to have to do is we're going to have to make that equal, and we're going to do that with a 2. Now, what that's going to give us is that's going to give us 4 irons. So I'm going to put 4 in front of here. And that's going to give us 8 sulfurs on the left. So we're going to put an 8 there. Now, 2 times 8 is 16, plus another 6, that's 22. So 22 divided by 2, the 2 from that oxygen, is going to give us 11. So we have a 4 to 11 to 2 to 8 ratio. Okay, so let's start off by putting out our reactants. We have FeS2. And if you recall from the other episodes, I like to do things across the page. It just gives us a nice clean look, and it also allows us to easily compare. So we have 300 grams of this, and we have 200 grams of this. Now remember, the decimal at the end of the zeros mean that those 2 of the zeros are going to be significant. And we need our molar mass of this. So we have 2 sulfurs at 32.06, and then in iron, we are going to get 119.97 grams per mole. Again, put the grams in the bottom to allow the grams to be crossed out. For oxygen, it's O2, so 32 grams, 16 times 2, and here we go. Okay, so if we do this calculation, what we're allowed to do is we can cross out our grams in both cases, and we're going to be left with moles, which is awesome, which is what we want. And we get 2.500625, 156 mole of FeS2. Cool. Now here we get 6.25 mole of O2. All right, so this is how much we have. Recall that we can say that we have 300 grams of FeS2, which is the same as saying we have 2.5 moles. It's just a different kind of currency, right? So one's in grams, one's in moles, but we have both of these. Now, next thing that we want to do is we want to compare. So when we compare our reactant, so mole of FeS2, we want to put that on the bottom so we can cross that out. In this case, mole of O2 on the bottom. We need to choose a product. And as I mentioned before, the product that we want to choose is the product that we're being asked for, right? We're asked to find the percent yield of iron 3 oxide. So let's use that in our comparison. So what I'm going to do is I'm going to put mole of Fe2O3 on the top, and the same thing, mole of Fe2 on the top, Fe2O3 on the top there. Now, where do we get these ratios? We get them from our balanced equation. So I'm going to put a 2 here and 2 there because they're both mole of Fe2O3. And we're going to put an 11 here, and we're going to put a 4 here. Now, where do we get all this? So again, the 2's that are here come from this 2 at the top there. This 4 comes from a balanced equation 4, and then this 11 on here becomes this 11 over here. Again, by doing this dimensional analysis, we can cross out all of our units, and we are going to get moles of Fe2O3. And what we end up getting is 1.250312578 mole of Fe2O3. And on this case, we get 1.136363636 mole of Fe2O3. Again, both we need in Fe2O3 because we want to choose the same product to compare which one produces the least of it. And what we can see is that we've produced less product in this situation. So the reactant that caused that lower amount of product is this O2. And so our O2 is going to be our limiting reagent. So we're just going to highlight that there. Okay, so now that we've discovered what our limiting reagent is going to be, we can cross this out, right? This is just a theoretical calculation that allows us to compare. But once we found the limiting reagent, we don't need this anymore. So I'm going to just rewrite this over here. I'm going to have 1.136363636 mole of Fe2O3. And I need to get it into grams because my actual yield is in grams. So I need my theoretical yield to be grams so that we can cross out the units. And so my mass of Fe2O3 is 159.70 grams per mole. And this is going to give us a mass of 181.4772727 grams. Okay, now we're not done yet, but we can actually round this off here because we are going to be comparing something with three significant figures. So we can actually round this off to three significant figures as well, 181 grams. Again, why? Because our original value here, the 200 grams, had our three significant figures. So this right here, what have we just figured out? This is our theoretical yield of Fe2O3. Now, as we saw before, percent yield is just actual yield divided by theoretical yield times 100. Our actual yield, as we got from the question, is 143 grams divided by 181 grams times 100. And so what we will get is 0.7900555249. And we're going to multiply that by 100. And if we round to three significant figures, we will get 79.0%. So that right there is our percent yield for this reaction. If we got 143 grams out of 181 grams, our percent yield is 79%, not too bad. All right, let's look at another example here. Now, in this particular case, the percent yield is actually already known and given to us, and it's asking for our actual yield. So we said that we can't calculate actual yields. What's going on? Well, maybe these individuals have done this process a number of times. They've tried to keep everything as consistent and as perfect as possible, and they keep just getting an average of 42% as a percent yield. And so now they can apply that and say, well, this process, regardless of what we do, is going to be 42% yield. So what do you think our actual yield might be if we do this process again? And so in this particular case, we have manganese dioxide reacting with hydrochloric acid. And it's asking us for how many grams will be produced. Again, now the key word, will be produced. So what is our actual yield of this if we have a percent yield for this process that's 42%? So remember that in percent yield, we need actual yield and theoretical yield. We are given percent yield. We are asked for actual yield, which means that we need to calculate theoretical yield. And in order to do that, we need to do our limiting reagent. In order to do that, we need a balanced equation. So let's start off with our balanced equation. So we start off by looking at this, and we can see that we have two hydrogens on that side. Again, I look at the oxygens, and I'm seeing that I have one oxygen on my left side, on my right side, and two oxygens on my left side. So I'm going to put a 2 in front of this H2O there. And that means that I'm going to have a 4 of this, and 4, let's see, Mn, O2, O2. 4 hydrogens, 2 times 2 is 4. 4 chlorines, 2 plus 2 chlorines is 4, and it looks like I'm balanced. So I have a 1 to 4 to 1 to 2 to 1 ratio. Now, I didn't pull the ratio on the previous question just because I didn't have any space, but it's nice to do this because, again, you don't need, once you have this balanced equation, we really just need these ratios. That's really what it's all about, especially for stoichiometry. So we have that now. Let's get started. So we'll lay out our reactants. We have MnO2 and we have HCl. We have 70.0 grams of this. And if we calculate our molar mass of manganese dioxide, we should get 86.94 grams per mole. That again will allow us to cancel out our grams and be left with mole, which is again what we want. Now here we are given a volume and a concentration in molarity. Now remember that this big M represents mole per liter. So I like to expand that back out so I can cancel out my units. And this ml just won't work for us because molarity is in liters. So we're going to have to convert that 500 ml into liters, which is going to be 0.5. Now, our equation is C is equal to N over V, but to find moles, we have to rearrange it to C times V. So our concentration is going to be 7.00 expanded mole per liter, and our volume is 0.500 liters. Now, I like to keep the significant figures here because there was a dot there. I like to keep the significant figures there so that they carry through and I can keep track of them. My liters will cancel out here and I'll be left with moles. So let's do this calculation. What we have up here is 0.805 0.152979 mole, and that's going to be of MnO2. I like to keep my units and my species kind of in the mix so I don't get confused with all these numbers. And then when we look at this one, we'll have 3.50 mole of HCl. All right, comparison time. So I want to get rid of my mole of MnO2 here, and I want to get rid of my mole of HCl here. We have to choose a product to compare. But again, it's asking us for how many grams of Cl2. So it's asking us for the actual yield of Cl2, and it's also telling us the percent yield of Cl2 is 42%. So let's choose Cl2 to compare it for our theoretical yield. So I'm going to put the moles of Cl2 on the top on both situations because we need the same react product to compare. And we have 1 here, we have 1 here, we have 1 here, and we have 4 here. Again, where did we get all these? We can see that the 1 here is going to be the 1 for both of these. The 1 for the MnO2 is going to be the 1 for the MnO2. And then the 4 for the Cl is going to be the 4 for the Cl there. All right, and now our moles of MnO2 will cancel out, moles of HCl will cancel out, and we'll be left with moles of Cl2. This is a 1-to-1 ratio, so our answer is going to be 0.805152979 mole of Cl2, and here we're going to have 0.875 mole of Cl2. Cool. Now, which one is the least produced? Right here. So we can cancel this one out. That's no longer valid. And our limiting reagent is therefore MnO2. It's the reactant that produced the least amount. So now what we need to do is we need to get this into a unit that's appropriate for our question. It's asking us for how many grams. I'm just going to rewrite this over here. 0.805152979 mole of Cl2. And I need to convert this into grams. So we need our molar mass of Cl2. So moles on the bottom, grams on the top. And 35.45 times 2 is going to be 70.90 grams per mole. Our moles will cancel out, and we will get 57.0853461 grams. Just like in the previous question, we're going to be doing a division, so we can go back and we can say, hey, look at, we have 3 significant figures for this, so our final or sub-final answer will be 57.1 grams. And once again, this is our theoretical yield. Now, how we find actual yield is going to be a little bit different. We need to look at our original equation. Percent yield is actual yield divided by theoretical yield times 100. But we are looking and trying to isolate for actual yield. So we have to manipulate this equation somehow. What we can do is first get rid of the 100, so we can divide both sides by 100, right? And this will give us percent yield divided by 100 is equal to actual yield divided by theoretical yield. Now, once again, we want to get rid of the theoretical yield so we can multiply both sides by theoretical yield, causing them to cancel out here. And now we have our equation. I'm just going to rearrange it to show that it's showcasing actual yield. So percent yield divided by 100 times theoretical yield. Now you can also rewrite it as percent yield times theoretical yield divided by 100. It's going to give you the same result either way. I'm just going to choose the first one. So let's plug in our values. What we got is we saw that there was 42.0%. So I'm going to turn that back into a decimal, and I'm going to multiply by a theoretical yield, which was 57.1 grams. And if we get this, we get 23.982 grams. And if we round to 3 significant figures, we'll get 24.0 grams. And this again is our actual yield. So based on a percent yield of 42% and a theoretical yield of 57.1 grams, what we can expect is about 24%. And again, if you bring it back to the test, let's say, for example, you had a test at a 10%, a test that had 10 marks, and you're pretty consistently a 90 student, right? Then you could say, okay, well, I'm consistent in 90s. I get around the same thing. My average is about a 90. So out of that 10, if I apply that 90% to that theoretical yield, which would be the 10, 90% would be the percent yield. What can I expect to get? I would get 9, right? And that's the same idea. So give this question a practice. It's the same idea. You can pause the video, and then when you're done, you can come back and you can unpause it, and we'll talk about the answer. All right, welcome back. So what we had to do here is we had to formulate the equation by ourselves. So we were shown that we had aluminum metal and copper 2 nitrate, and that's pretty much it. Now, there was a hint that, yes, we have to find copper, but what we have to recognize is that this is a single displacement reaction. So go back, if you don't remember how to do those, you can go back to our previous lessons and look at those. But one other thing that we have to look for is that does this reaction actually happen? And as we've seen in the past, to determine if a single displacement reaction has actually happened, we have to look at our activity series. And in this case, the aluminum was higher than the copper that it was trying to replace on the activity series, so the reaction does occur. Everything else is the same. We set out our reactants, and in this case, again, we have a concentration, so we need the volume in liters. We expanded the units to be able to cancel out the liters on here and be left with moles. Once we got the moles of each, we chose copper to compare because it's asking for what is so if the percent yield of copper is 80.07, what is the mass of that metal? So we want to also calculate the theoretical yield if we're trying to find the actual yield of copper, and we're given the percent yield of copper. So we put copper on the top, we put our reactants on the bottom that we want to cancel out. We get all of these ratios from our balanced equation, and we get our values. And what we can see is that aluminum is the one that produces the least amount of that product. And so that aluminum is going to be our limiting reagent. We're going to take that back. Remember that we're trying to respect it in grams. So if we want the actual yield in grams, our theoretical yield also has to be in grams. So we take the mass of the copper, the molar mass of copper, we get 16.5 grams, and we use the same equation that we had before to calculate that we got 13.3 grams as an actual yield. Hopefully that helps, and we'll see you on the next one.